My name is Reinhard Simon. I'm working here at the NIA, and we will have today first day of small introductions also from you. Next will be just a quick overview of the days we have been organizing. Mainly each day is on one big topic, and we go from simple to a little bit more application-oriented bioinformatics tools. So we will start out with very basic things in Linux and Unix today, and then we will have more application focus over the last few days. So we wanted the course to be very practical, but without theory there's also not much to learn. So we will have mainly in the mornings some introductory lessons, but occasionally a few days where we also have in the afternoon some demo or short topic which is kind of interesting and related we should know about. Another request we heard early on from our prospective participants was opportunity to foster more the networking part, and one idea we had there was to allow everybody to present briefly a little bit more about his work or research interests in kind of lightning talks. So this will always take after lunch, and so it should be really very short, so 5 slides, which is more or less 1 minute each, so it's 5 minutes for you, and then we should have 5 minutes for questions, and it would be 3 in a row. So if you haven't registered yet, please approach Sandra, I think, to keep the record, and or Andrea, I think, Andrea, for your talks. And yeah, so the next part is the list of topics we have now for each day. So today will be with Linux, starting with Juan Montenegro. And tomorrow we will learn about programming basics, mainly with R, but getting a little bit of first impressions with some other languages. On Wednesday, we will then start out with best practicing for making your bioinformatics work reproducible and reusable to a maximum. And then we will have another day on design of experiments. And then on Friday, we will start with NGS and genome assembly. So this is for the first week. And the second week, we will go to alignment. Monday and Tuesday, transcriptome analysis, and systems biology on Wednesday, and GBS and SNP discovery on Thursday, and GWAS on Friday. And the last Friday will only be basically half a day, because on the afternoon we'll be basically closing down and also taking your impressions on the course and continue improving and so on. So this is the basic outline. You have all, I think, the full program in your hands. What else? Yeah, I mentioned now the lightning talks. So we don't go this. And yeah, logistics. I think there are 2 main points. We wanted to make sure that we have a minimum dependency on networks and systems. So there's a bit of a challenge, as you probably know. Bioinformatics nowadays is usually concerned with very big data, and you need really big servers if you want to work with real data. And we don't have the resources here right now. And on a laptop, we usually can't do this either, so we stick to very small examples. And also we focus mainly on using for most of the application-oriented examples R, basically. So we will have Linux only basically today. No? But if you want to learn more about certain things, I think you're always welcome to ask one mainly with our specialist tutor this week here. So one constraint, even with using like a virtual box on your machine, is also the memory. So just big check. Who has 16 gigabyte RAM on his machine? 16 gigabyte RAM on the laptop with 8 gigabytes. That should be everybody. Yeah. So please check how much gigabyte you have, because below 8 gigabytes is usually not really possible to work. So you will need to work probably with somebody else. Who has Mac? So 1, 2. Maybe you can also help those people to set up things. And yeah, so for every other questions, I think logistics in general with Sandra and Andrea. And with that, I think we can start. If you want.
All right. Good morning, everybody. Thank you for joining us in this training course. The first part of this day is going to be just a theoretical introduction to Linux system, Unix-based systems. How many of you are used or mostly work on Windows or Mac? All of you? Have you guys ever touched Linux or Unix-based system at all? You have. All right. You have as well. Yeah. So since we have very different levels of starting, we're going to start from scratch. What is a Unix-based level? What is it? Why is it preferred for most of next-generation sequencing and big data analysis? And yes, that's basically the first part of this presentation. So what are we going to talk about in this first half an hour? The first thing is what is Linux or what is Unix? Then we're going to talk about what are operating systems. You're all familiar with them, even if you don't know exactly what they are. What are the advantages and disadvantages of using Unix-based systems? Then we're going to teach you some basic exploration, manipulation commands on the command line for Linux. We're going to learn a little basic stuff of scripting in Bash, and also how do these machines and this Unix-based system are mostly used in big servers that have huge amounts of RAM. We were just asking around how much RAM each of you have. If you have 4 gigs, 8 gigs, 16 gigs, etc. When we talk about servers, we're talking about 64 gigabytes of RAM, 128, 256. More often than not, lately the biggest servers have between 2 and 6 terabytes of RAM. That's 2,000 gigs or 6,000 gigs of RAM. Now you may wonder why is all this hardware important? It's because it lets you handle big chunks of data, which is the kind of data that's being produced lately. Not only by bioinformaticians, not only by next generation sequencing machines, but also by all sorts of, all branches of science. Astronomers, they use their own models, they have to do like image analysis. The weather people, yeah, they need to run models to predict the effects of climate change, or just predict the effect of things like El Nino on the rainfall and on the drought across different continents. So all these take a lot of information in, and they require a lot of time to work, to load, to display the results. This is all called big data. Yeah, and there is no easy way to handle big data on Linux, on Windows, or in Mac for that matter. Have you ever tried to open, like, I don't know, a 300 megabases Excel file table, or 1 gigabase table? Just try to double click a big Excel file, and you'll run into memory issues. You'll run into big sluggish machines on your personal laptop. It's very, very unlikely that you're ever gonna have the time or the memory or the specs to actually look into that. Yeah. In Linux, you don't have to exactly look at the entire, open the whole thing, the whole big table into memory. Yeah, you can just start looking at it from different parts of the file without actually opening the whole file. And that helps you a lot, because that helps you automate the way you want to analyze the data that it's inside that table. And instead of just copying all the table, putting it into memory, and making sure that you have enough resources to do it, you just take small chunks of the memory, sample across the whole file, and you start analyzing those chunks. And you start getting some general overview of what's inside this data. So yes, when we talk about big servers, we need, these are usually shared resources between different branches of science, and that requires some resource management so that one single user doesn't use the whole system. Yeah, we use resource managers. So what is Linux? Linux is the most used and best known open source operating system in the world. What does this mean? Basically, this means this is a program. It's one of the first things that run in any hardware you have, in any laptop, in any server. The operating system is the first thing that run. And the fact that it's open source means that it's free. You don't have to pay a dime for it. In contrast to Windows or to MacOS, that you do need to pay a fee to use it. Linux and Unix-based systems, you don't have to, well, most Unix-based systems, you don't have to pay for anything. The most popular one for desktop is Ubuntu. In this case, we're going to be sharing with you one operating system based on Ubuntu called BioLinux, which already has all the tools for bioinformatics analysis, or most of the tools for bioinformatics analysis that you'll ever need, pretty much, unless you're developing your own tools. System that, well, we have a small picture of all the different Unix-based systems that you on the right. Yeah, the favorite so far is Linux. And it was developed for personal computers. And the favorite from all the Linux distributions that you'll find, it's Ubuntu. I just told you that Unix is an operating system, but what is an operating system? An operating system is something like Windows. It's something like your MacOS. It's something like your Android. It's the one program, or well, a combination of different programs, yeah, that merge together in order to give you an easy access to the hardware you have. For example, if you wanted to use your camera on your mobile phones, yeah, you just have to go to the app, press a button, an icon, and it will automatically access the camera, turn it on, and you'll start focusing whatever you want. It's that simple, right? Yeah, but in the background, it doesn't work like that because everybody has a different phone, and every camera spec is different, and every connection is not the same in the hardware, in the actual manufacturing of the mobile. How do you make it all seem similar between different devices, and at the same time it works? It just works out of the blue. Basically, that's what the operating system does. This is the connection between the hardware that you have, yeah, and the interface and the final user, what you actually see. Yeah, that nice Windows array in Windows 95, or the start button on the Windows on Windows XP and forward, or that nice display on the MacOS. Yeah, all that is just handled by the operating system. And in the background, every time you just click or double click an icon, yeah, it is started to run programs, and these programs are specifically tailored to handle the specific hardware that you have. When you install an operating system on a computer, you cannot simply copy it over to a different computer, yeah, because the different computer will have a different hardware, and the configuration, the command calls, the input and output reads are gonna all work differently because they have a different hardware behind it. So you always have to reinstall things from scratch. So yeah, basically the operating system works first at this level, which is the program control. That is, it's a kind of a resource manager. It makes sure that two programs don't access the same memory space. It makes sure that two programs don't use the same processor at the same time, or if they do use the same processor at the same time, they do it orderly. They manage input and output, that it's reading from the disk and writing into the disk. When you create a new file, you're writing into a disk. When you're loading a file into memory or opening a file, any file, Excel file, whatever you want, you're reading from the disk. The file system is the way the files are being stored on your hard drive. It also well, the communications, that is different external devices that can be plugged into your computer. Also, error management. Whenever a program fails to run, yeah, it needs to send the user a warning. Hey, this is not working, and this is probably the reason why. And all computers store a log of what failed when you try to run something. Resource management, as I was telling you before. Auditing and security. Security is, as you've seen, just to prevent any possible glimpses where your personal information may be exposed to external attackers. You never know. So basically, all this is managed. It's handled by the operating system. The operating system does the machine language calls. This is not something that we are meant to read, because it doesn't make sense when you read it. It's just the ones and zeros that we've been taught that computers use in the background. Yeah, this is what the operating system is going to handle. Yeah, and then the user interface. Basically, it's make all these internal decisions and connections and communications seem as simple as just double-clicking an icon or just pushing one part of your screen. That's the user interface. Now, on top of that, you can install all the programs. And that's the apps that you use on your phones. For example, if somebody has installed Office on your Windows, on your Macs, yeah, that is a program that is on top of the operating system. Now, the operating system needs a little bit of RAM. That is, needs to load some things into memory so that it runs smoothly. Yeah, this is called the overhead memory usage. Why is it overhead? Because that means that if you have, for example, an 8 gigabases of RAM memory, which is random access memory, this is the fastest memory you'll have in your laptop or in any computer. That means that a little bit of that is going to be used by the operating system. Windows usually is the operating system that uses the biggest chunk of the RAM. It has a lot of overhead. That means that you have less RAM available to run your own thing, the programs that you really want to run. On the other hand, Linux or Unix-based system, they have very little overhead, which means that you will have a lot more space to run bigger programs. So, advantages of Unix-based system. Some of them I've already mentioned. First, it's free. You don't have to pay anything for it. It is high performance. It's highly scalable. It is very flexible because it is very easy to download drivers for any new hardware that you have, although most operating systems are pretty good at that. It offers a lot of stability. That means that you will not run into unexpected errors. That's something you always want in your operating system. Compatibility. In contrast to Mac, for example, usually Mac laptops and iPhones, etc., they only run with Mac things or Apple devices. Yeah, it's not easy to have it compatible with other kind of devices. But Linux is the most compatible of them. It will accept macOS, it will accept Android, it will accept Windows, it will accept everything. Everything can be used under Linux system. Multitasking. It's better multitasking because it handles the multi-threading and threading of the cores better than the other operating systems. And security, basically it gives you full control of what's running in the background of your computer. Usually you don't realize what's running in the background. Windows user will probably notice that sometimes it takes a lot of time to finish loading just the initial screen. That's because there are a lot of programs that are starting up in the background. Your firewall, your virus detection scan. You probably have some some daemon, or there are so many things that run in the background. I cannot mention them all by heart at the moment, but yeah, all these things take a lot of time, and they also take a little bit of memory out of your hardware. Yeah, Linux, you don't notice, and it's not easy in Windows to actually tell, hey, kill these processes because I don't need them for my current purposes. In Linux, you can. You have full control of what's going to run, what's not going to run, and what is happening in your background. That also gives you that extra security, that if you have a virus running in your background, it's easier to just stop it. In Windows, you can't do it as easy as that. You will not notice what's running. What are the disadvantages of Unix-based system? Well, this is something people who have already used Linux systems have already noticed. There's a very steep learning curve. Yeah, it's not easy. Well, it wasn't. It's a lot better now, but to get used to the feel and the and the display of Linux. Even though it looks very much like Windows right now, yeah, but you have so many options and you have so many tools available that it's difficult to actually get to use it properly and take the most advantage of it. It takes a lot of time to learn this. Well, as I was saying, it's not very user-friendly. That is, when you're used to other operating systems, it's difficult to just jump back. If you've ever, for example, those who use Windows, if you've ever seen an Apple machine, yeah, you take a while to get used to the display, where things are hidden, how to run programs, etc. The same thing happens with Mac users who go to Windows. It's hard to get used to it. It's the same for Unix, basically. It's a different display, it's a different feel altogether. It can be confusing for beginners because you do need to understand how the operating system works from the roots to actually get the most advantage out of having a Linux distribution. There are way too many options, so it's so flexible that you have a limitless numbers of tools and commands that you can use in different ways to achieve quick analysis of very big data files in very short time. And finally, they have, this is a good and a bad thing at the same time, there are frequent updates, very frequent updates. These are security updates, new versions of some of the software that you've installed, all these kind of things, they take a time. Every time you turn on your Linux-based machine, you probably will have an update to run before it. It doesn't work like Windows that you have one every 3 or 6 months. No, this one you can find one every 2 days. You'll find a new update. So now, how does Linux present itself? This one is going to look ugly, yeah, but this is not the final look of Linux. Linux right now looks pretty much like a Windows user interface. Basically, you have your mouse, you have some icons, you can double click, open files, you have a file manager. It all seems natural, except that you need to work a little bit on where to find these tools. But the most powerful tool of all Linux is the shell. The shell is this black screen that you've probably seen in hacking scenes or in other movies, yeah, where you just write everything. You send commands on the command line, you type them down, and you find where you are, what you're doing, where you're going, open the file, just show the first part of the file, show the last part of the file, you move the files around, you mess with the file, you make calculations on the file without actually having to open the whole file from scratch. That is what we can do from the shell. And the most commonly used shell on all Linux, you have many different flavors, is the bash shell, the born again shell. You have, as I was telling you, you have many other flavors. This bash shell is something that you will also find in the Mac users. Apple also has this command line prompt. I don't know if you've ever used it, yeah, but if you look for command line or for prompt, you will find also a black screen, and in the background they'll have this. The bash shell is what they call a programming language or a scripting language. Basically, you can put commands there, and you will start navigating your operating system or all your system file from the command line. So a shell, as I was telling you, it's pretty much the same as having a visual or a graphic user interface. As just the same things that you can do with your mouse, double-clicking here and there, yeah, you can do the same things just with your keyboard. As I was telling you, Bash is the default interpreter in most Linux distributions, and it has many useful extensions. For example, it has autocomplete, where you don't have to finish writing what you need to write, because the shell itself will guess based on where you are and what you're trying to type on the first few characters of whatever you're writing. Redirection, where you can tell each command where to send the outputs of a program. If you want to send it into a file, create a new file. If you want to send it on the if you want to display it on the screen, just put it on the screen. If you wanted, if there is any error, you wanted to log it, so you can send it to a different logging file. All these things, you can do it there. And finally, piping. Piping is concatenating several different commands so that you do a very complex analysis in one single go, in just one single line. For example, you have a huge table and you want first to sort it based on column number 5, then you want to pick only the first 10 hits, then you want to filter based on e-value, then you want to I don't know, I can think of many examples. Yeah, then you want to randomize the sorting, then you want to see how many duplicated lines you have, and all that in one single step, in one single command line, well, in one single piping command. Yeah, you can do all that very easily. So you can handle huge files and reduce them in size in just a matter of minutes, which is something you cannot do easily on Windows. Finally, a standard error and standard out. This is basically something that all operating systems have, all shells have, but we don't usually handle them directly. A standard STDR means a standard error. That is a special message or a special device through which an error message appears. If a program runs smoothly with no problems, it will give you a signal of 0. That means no problems were found on that standard error. If there is an error, a program will send you a warning or an error signal through that device, yeah, and you will be able to log and see, hey, yeah, what was the error, and look into what kind of error you got. They usually have codes and descriptions of what the error was, so that you can, and this is something I will always recommend, you can always Google what your problem was, because somebody has already faced that problem before us. That's something it took me a lot of time to learn, because most times we think that, oh, how do I solve this from what I already know? When Google, and there are way too many forums in Google, usually a lot of people have already run into this problem, and most of the problems have already solutions. So if you ever have a problem that you'll find in a standard error, you will be able to solve it most likely. In my 7 or 8 years of in bioinformatics experience, I would tell you that only twice have I run into problems that were not faced by anybody else. Only twice. And they were reported as bugs, like, hey, this is something new that nobody has ever seen before, and I don't know how to solve it. Only twice. And it never got solved, anyway. So, a standard out. A standard out is the standard output of any program. So, let's put an example. Let's say you do a sort command. That is, you want to sort a file, right? And you say the file only has 5 columns. Yeah, and you say, okay, sorted by column 6 numerically. I want to order them from smallest to biggest number that appear on column 6. And the program looks at the file and say, hey, there's no column 6. Yeah, so your output will be empty. You will see nothing in your output, but your standard error will tell you, hey, there was an error. On the other hand, if you run or sort it based on column 5, the program will see, okay, there is a column 5, so it starts sorting. Yeah, your standard error will tell you 0. All good, there was no problem. And your standard output will output the same table you just sent, the same file you just kind of opened, yeah, but in the order that you asked them to order. Yeah, if you wanted to sort it by numerically by using column 5, you will see that the new table will have that order, and it will do it very quickly. So let's look a little bit at the directory structure on Linux systems. Basically, all Linux systems will start with the root. What is the root? The root is, as I say, the root is where all the other directories are based on, or where they are placed. And why is this important and different from something like Windows? You usually see that Windows have, does any of you have like 2 different hard drives? Yep. Have you seen 2 different hard drives? Yeah, when you plug 2 different hard drives, or when you plug in a USB and then a new letter appears on your Explorer and say, oh, this is device E. Yeah, and you double click it and you start exploring what's in there. Yeah, so in Windows, they always assign a new letter to each of the devices connected. Yeah, each of the storage devices connected. In Linux, you don't have. It will look like as if it was all part of the same build. Every time you plug in a new device, a hard drive, a SSD, a flash memory, etc., it will immediately mount it. That's the name it's used. It will immediately mount it, and it will appear as if it was already part. It had always been part of your computer. You will be able to access it, and from the command line, you will be able to access it from the root. So let's see what are the main, the standard directories that appear after the root. So you have the root bin. Bin stands for binaries. Yeah, and binaries are basically executables in Windows. That's equivalence. All those things that you double click on Windows and they just run smoothly, those are binaries. Yeah, and those binaries are all stored here in root bin, etc. 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 Holds configuration files. That is the way Linux is gonna be behaving. Yeah, the way it's gonna set up their default directories, their default paths, where it's gonna look for libraries. All those default configurations are gonna be under etc. Then you have home. It works pretty much the same way home works for Windows. Yeah. Under home, you'll have several users. Yeah, and each user will have its own array of directories, personalized for each of them. More often than not, you'll have like documents, downloads, videos, pictures, and whatever other directory you want to create for yourself. Whatever you find more useful or you consider more helpful for whatever you want to do. Then you have opt. It's basically optional third-party programs are going to be installed there. Temporary, as the name, TMP, as the name suggests, it's only for temporary files. When you're running a program that produces a lot of temporary files, they usually get stored there. User, these are programs and libraries and most of the things that are specific for the user, for each user, but at the same time are going to be available system-wide. What do I mean by this? Is sometimes you have what you call shared library. That is, two different programs will need the same instructions, all right? And they need to load it. They need to find a common place to install this instruction, because you're not going to install these instructions or these libraries 3 or 4 times in different parts of the computer. It is a waste of space. Yeah, so you centralize that, yeah, and you put it on the user, yeah, and then you have user-specific binaries. You have user-specific libraries. Each user will have its own version of what they are using. And finally, var. These are variable files. These are files that are going to change every time you boot your computer. It is mostly system managed, so it's something you don't really need to bother about. So these are a few things that we're going to be looking at in the practical session. First, it's basic commands. How to find out where you are, move, change directory to wherever you want to go, how to display the contents of a directory, how to display the usage, the space that each of your directories and your files is using. Also here I should add, well, there are many, for example, grep. Grep is when you want to find a specific keyword or regular expression in your file, on your files. You have less when you want to display the content, the full content of a file. You have head and tail, which is commands that you use when you want to only display parts of the file and not the whole thing. You can also do manipulation of directories. You can create new directories. Wherever you have permissions, you can create new directories. You can move directories from position or move files from one directory to the other. The same thing you used to do with dragging an icon from one folder to the other. The same thing from command line. You can copy them. Instead of just moving them around, just create a copy in case you need it. You can change permissions. This is very important. And this is something that it's not easy. Well, it's easy to do in Windows, but most people don't and don't really care about it. But it's if you're working in a shared computer and you don't want other people to accidentally erase your files that took you maybe months to produce, yeah, you can change the default permissions so that only you can alter your files. Or maybe not even yourself. Maybe you don't want to have the opportunity to accidentally erase an important file. Yeah, you can change all those things with a command like chmod. Then you can also explore the files. You can use cat just to display the whole content of the file on your screen. More often than not, it's not going to be useful, but you can always pipe it. You can always use the cat to just send it to another different command. You can use head that I just explained, tail, which is the opposite to head. Instead of showing the first line, it shows the last lines of the file. You can sort files. You can compress files. You can VI files. VI files is just a text editor, yeah, that you can use from the command line, where you can modify the files, explore the whole thing, move with your arrows around and say, okay, this shouldn't be an E, this should be an A, and you change the A, or you can just do a small, simple command and say, okay, all the E's in my file, I want to change them for, I don't know, Z. Yes, and you can just, with a simple, very quick command, you can change all the letters, or one specific letter of the entire file. All of those letters can be changed like that. So yes, and you can also remove files. Now, these are the basic commands that we're going to be learning on the practical session later today. Then we will be learning bash scripting. What is bash scripting, or what is scripting altogether? Once you dominate these commands, once you dominate the shell script and you're familiar with the commands that you're going to be using, you usually will run into situations when you run the same group of commands over and over and over and over, because you want to process different files in the same way. For example, first you want to see the head, then you want to count the number of rows, then you want to count the number of words, then you want them, for example, you want them to give you a total sum of the column number 3. And then you wanted to have an average size of the word length in the whole document, yeah. And you'll see that there are a set of commands that you use more often than not. I said, yeah, it would be easier if I could just tell them, hey, repeat all these commands one after the other in this order, so that this thing that I used to write 6, 7, 8, 15, 1,000 commands one after the other, I don't have to write them every time. I just put it in a file, in a small script, yeah. And every time I wanna run the same sequence of commands, just activate that file as if I created my own binary, my own executable, yeah. This is what scripting is about. Basically, it's giving a sequential list of commands that you know you've already tested, that they work and they will produce the results that you're looking for, putting them all in a single text file, yeah, so that next time you need to run the same list of commands, you don't have to write them all again. You just can call it and say, okay, run this program or this script on this file, and that's it. That makes life a lot more easier. And this is the same principle. We're going to be using bash scripting because we're going to be using bash a lot more than anything else. But this is the same principle that works for most other interpreted languages like R, Python, Perl. You can just, once you learn the basic commands, you can just create your own sequence of commands for a specific purpose, yeah, put them all together in a single file, and that is your program. That is a user-defined program. That's something that you created for yourself because it was useful for you, and it will produce the results that you wanted to look at. And you don't have to write them over and over and over again. Of course, people have been doing this for decades. Yes, so this is not something new, and we will find a lot of trouble. We run into a lot of troubles when we start doing this. Yeah, but these are all issues that have already been addressed, and we will be able to address them in the practical session. Also, this is basically the reason why there are libraries. You may realize that I've mentioned libraries in previous slides. What are shared libraries? You have to load some commands, etc. It's because people have already put together a lot of commands into small, simple programs. These are called libraries. Yeah, it's, for example, okay, most people like to sort things. And sorting is not a straightforward thing. You need to compare each of the elements of a list to each other, determine which is bigger, which is smaller, or which is longer, which is shorter. Yeah, and once you have already done that, then you display the new order that was asked. A lot of people have done this before, yeah, and a lot of people have spent a lot of time trying to optimize the best way to do it. Yeah, reduce the memory, the memory overhead, increase the speed, etc. All these things have already been optimized. Yeah, and somebody created a library and say, all right, yeah, let's create this command called sort, which follows these instructions, which are optimized for this kind of process, yeah, and put them in the library. And there, next time somebody wants to access a sort command, the only thing is the program on the operating system is going to do is, under the hood, is going to look for the right library, say, okay, this is the one I'm looking for, and run it smoothly. This is what libraries were created for. This is just scripting and putting these commands into a single file. This is exactly what the start, the beginnings of trying to build your own libraries, custom libraries. So yes, it's a sequential list of commands. They can be saved into a file and they can be executed as a program or simply manipulated like a regular text. Every time you want to improve it, you can just go to your text editor and change it. Are we on time? We're close to the end. So piping, the one thing I was mentioning. Every time you run a command, you'll get basically two outputs. One is your error output, and the other one is your real output, your standard output, right? Are you guys following? Do you have any questions so far? Well, feel free to ask or interrupt me at any point. So sometimes, well, you have a command and you'll have two outputs. Piping will let you use the output of the first command as the input to a second command. For example, we discussed head and tails. Have you guys all seen what a blast result looks like as a table? Have you guys run blast? Right, most people have, right? So when you see the table, you see that there's several columns. Sometimes you want to do some filterings, and you say, all right, based on the e-value, I only want a result or hits that have an e-value below 1 to the minus. So you first filter it. What do you use for filtering? You use something like awk. I'm going to teach you that later as well. Awk, and you say, okay, from the column of the e-value, just pick those that are below this e threshold, and you set it out. So you set the first command, filtering, yeah, so the regular output, the standard output, should show you a full table, a new table with only the selected lines. But you say, nah, it's still too long. So let's sort it. Let's sort it by score. So then you said, instead of showing you into the display, into the standard output in your screen, seeing a whole big table, you say, no, let's sort it. Let's sort it by the score. So you pipe, after the awk command, you pipe a sort command. What is a sort command? As I was telling you, it sorts the file that you're giving it. But you're not giving it a file. You're giving it the output from the previous one. So first you filter, and the second is sorted. So the program internally starts comparing everything. It shows what the new order is, yeah, and it's gonna display it. And from this graph, it looks like that's where it ends. But you can add another pipe. And you say, okay, once it's sorted, it hasn't actually reduced the number of lines I'm going to show. Yeah, so I want only to show the top 10 or the top 5 hits. So I sorted by score. So ideally, the biggest, the highest score are going to be on the top of the new file. So I say, all right, then just show me the head. Then you pipe it to a head command. And what you're going to see is a filter table, yeah, that shows you only the top 5 or top 10 scoring hits for a specific blast result. So you've already filtered. It could be a huge table, and you've already filtered it and showed the best hits for it, just using this a single line, a single command line. So you can concatenate 2 or more commands where the input of one command is the output of the previous one. It's useful for quick analysis of complex files and allows for easy exploration and basic manipulation of the files. Please keep in mind that you can always redirect whatever you have already filtered into a new file. So you don't have to repeat all the things from scratch. Yes, yes, you can. Yes, you can. So you mean for sorting? Whatever you want, as many as you want. Yep, as many you want. There are many tricks to use that if you're planning to use it for filtering or just playing around with blast tables, for example, or hammer table or any other like tables of similarity scores, yeah, you can use as many fields as you want. And you can use even different rules for each of the fields, not necessarily numerical order from higher to lower. You can use operations. You say, okay, I want to order based on the difference between a score, bit score and total score, for example. You can do that, yeah. So what's the difference between pipes, the last thing I just mentioned, and scripting, putting all into a file? Basically, the pipes, commands that you use in a file cannot be saved into a program, into a script. So you have your pipe, yeah, you can put it as part of the script, but usually it's just a one line. It's just one line of a quick analysis, a quick checkup of what the general structure, what's the feel of the file you have in front of you. So it's really useless to save it into a file. You usually don't do it. Compared to scripts, the scripts can be saved into a file. All the sequence of commands can be saved into a file and can be repeated very easily. Pipes, it's not possible to save intermediate files. For example, as I was telling you, first you filter, then you sort, and then you just display the head. Yeah, those intermediate files from the pipe, you cannot save them. Whereas if you did the same thing with a script, yeah, all the same steps with a script, you could save the intermediate files and take a look at them later if you want. You can use a script inside a pipe. So if you've already developed a script, yeah, and you want to run that script as part of your pipe, that is as one of the commands between each of the steps, you can do it. Yep. And you can, oh, sorry, that should be UV, not DV. So we can use pipes inside a program. Yes, you can use pipes inside a program, but it's usually not recommended. Pipes, you cannot create variables. Variables will store a specific values inside a program or inside the system. Yeah, pipes will not create variables, but they can use system-wide variables. So if you already have a variable defined, yeah, the pipe can use it, but you cannot create one. Whereas the script can create and use variables that are already exist there. Absolutely. So variables can be anything you want, to be honest. The most commonly used variables, yeah. So the most commonly used are integers. That is integers, numbers. You store numbers into variables because you're going to use them later. It's something informative from your program. The other thing you usually store as variables, strings. Just strings of characters. This could include alphanumeric numbers or even non-alphanumeric or non-ASCII symbols, like Chinese characters, etc. Those can be stored in variables as well. Other kind of variables are arrays. It's list or an ordered list of the two basics that I just mentioned. For example, a list of integers. You have a sequence 1, 2, 3, 4, 5. Yeah, so that is an array. That is a kind of variable. Then you have dictionaries or what they call hashes. Yeah, which is like how to explain it? Related arrays. So you have two arrays. One is the keys and the other is the value. Yeah, and you say, for example, I want to look in this variable. I want to look the value of the color orange. And the value of the keyword orange will be the hexadecimal code for orange, for the combination of orange in RGB, in red, green, blue codification. Or you can put, for example, every time I mention the name Juan, the value will be his last name, Montenegro. Or for each of you, you will have a list of all your first name and then your last names. That kind of things. And all these variables what we call memory, RAM. That's why this is important, and that's why it's also important to make sure that you have usually most RAM available. Because when you analyze big tables, yeah, and you start loading more and more of these variables into memory, yeah, they are going to be filled. If you have little memory or little RAM available, your system is going to crash because they don't have anywhere else to put that variable that you're saving. So the bigger the variables you're trying to save, the more memory you're going to need. Well, I mentioned this already, scripting in all languages. There is a difference that we can talk later on if you are interested between scripting languages and compiled languages. On the left, you'll have a list of scripting languages, and then you have time to write more compiled languages. But the main difference is that compiled languages are usually faster and better at memory managing, but they require a lot more programming experience. It's not easy to program this in this, for example, C or C++. Whereas the scripting, like Perl, Python, R, etc., they are very easy because the commands are usually they are usually like commands you would use for speaking, like sort. You know what a sort means. Yeah, if it's it's a conditional command. So these kind of things. So finally, as I was mentioning, when you start using servers, you have a lot of resources available. And sometimes naive users will start running huge programs that will try to consume as much resources as possible. I myself, I have run programs that use 2 or 3 terabytes of RAM, yeah, on a 1 terabyte server machine. Well, that's when I was just starting. So I crashed the system and I crashed all the programs that were running on that server. That were not only were they from my group, they were from different groups and programs that had been running for days. Yeah, and I crashed them all just because I didn't know how to use it, and just because I didn't know how to use a resource manager. A resource manager, basically what it does, you submit a command or a program to run, and you put it limits. You say, okay, you start running this program, but if you reach, for example, this amount of memory, yeah, and the program wants to ask for more memory, you kill it. You don't run it anymore. If the program tries to use more processors, more CPUs, yeah, kill it. Don't let it more. If the program is running for 2.5 years, please kill it. It's not going to finish ever. Yeah, that kind of thing. So that's the way the resource manager handles things. We have very naive resource managers in our operating systems. You will be able to see them on Linux. It's very easy. It's a very easy command to see what's running in the background. But these are more complex for more complex resource manager. One of them is slurn, which hopefully we'll be able to take a look at by the end of today. And that's it. Thank you very much for your attention. If you have any questions, please feel free to approach.